Great, thanks everyone for coming. And yeah, this is a very awkward 5 seconds with the recording. So I'm Suhail. I'm an assistant professor at the University of Birmingham, and we have a transients cosmology, a small group which includes 2 students who are graduating. So obviously in supervisory duties, I hope people can actually see my slides. Wait, they can. I don't know why Zoom has just. Yeah,
no, they cannot anymore. Okay.
Great. Sorry. I don't know what I have to do.
Internet.
I don't know if it was internet, it was Zoom, it was.
I've been disconnected from.
I don't.
Yeah, you don't have internet. You don't have internet because you are there.
No, I've got shipped out as a Zoom because I don't have what it is.
Maybe transfer, yeah. Maybe we can try to use that one. Or what is it? But I don't know. Yes, but this cable. Wait, this cable.
Yeah.
So,
Or maybe if there's like a Wi-Fi, maybe use the society here.
Worst case, I will send you. How do I send you?
Oh, question.
I can send you however. I'll just send you my keynote. Yeah.
Send me the keynote. Yes.
Yeah,
Devotion, or which is the sound?
No, here's the.
Yeah, computer में जो व्यवस्था दिया है, the slides, right?
It should work. Just not have enough room. Yeah.
Thanks.
Let me know if I should airdrop it to you. Oh, you want mine?
Yeah, that's why the keynote.
Yeah.
You say no reply.
Else, compartir pantalla. You cannot share your screen. That's the because you're in Zoom, so you're connected.
Yeah, but I think
for now.
I don't know. Everyone just doesn't like me for some reason, and when I need it most,
Okay. You cannot connect.
Do you know if there's a way? I know, but it's not.
I think it works on.
Yeah. With the third, that's gonna work, right?
It didn't work.
Okay. Well, we can retry.
Okay.
Thanks to his. All right. Apologies for technical issues. Take 2. It's fairly appropriate that when you're talking about time delays, you're going to expect some amount of delay between actually starting the webinar or not. So strongly lensed supernovae are my new sort of very excited passion to use them in cosmology. some of the work that I'll be showing today is part of sort of generation one of students in my group who are now graduating their PhD and their master's respectively, and have been very excitedly working on the different aspects of time delay cosmography. And we have a group that's set up to start applying these methods now to LSST. Over the next roughly 40 minutes, I'll start with like a brief motivation, like why are we so excited about lens supernovae and what are the cosmological questions that we want to answer? And then we move towards what lessons have we learned from current discoveries. Lens supernovae, which were originally actually thought of as being cosmological probes 60 years ago. So Suhail actually wrote a paper in 1964. But now, like after the first discoveries in the mid-2010s, we're really getting to making this a reality. And we are at the cusp of the stage 4 of next generation cosmology surveys. And the Vera C. Rubin Observatory is getting ready for data taking. So we're preparing for the inference of time delays and ultimately cosmology by resolving systematics and lens modeling. And lastly, I'll talk about the problem of dark energy and how lens supernovae can actually give us a window there as well. But let's start at the sort of very zeroth order, and apologies that this is very basic to everyone, but just to set the scene and get everyone on the same page about why we're so excited. So we have a standard model in cosmology where in lambda CDM, about 70% is dark energy given by the cosmological constant, about a quarter is dark matter, and ordinary matter is just 5%. And this model has worked exceedingly well to explain both the early and the late universe probes. So going from the CMB all the way to large-scale structure, and then very recently also type 1a supernovae and the baryon acoustic oscillation. However, now what we see in the recent sort of years to the last decade is that we're getting some evidence. So the plot on the right-hand side is showing the dark energy equation of state, or the pressure to density ratio, and its time evolution. So the present day value on the x-axis, time evolution on the y-axis. And this standard cosmological constant scenario is given by that black star. And we see that depending on what supernova compilation you use, there are different levels of significance that are hinting at possible evolution of dark energy. Along with that, we also know that like there are theoretical problems with this existing model, right? Like we don't have like a physical understanding of what dark energy and dark matter are really driven by. So we have issues like fine-tuning and the cosmological constant, the coincidence problem. And we also have seen like a more sort of mature problem now, which is that the prediction of the Hubble constant from the early universe and the direct measurements, most of them in the local universe, don't seem to agree with each other. So while like this model has worked really well, now we're seeing certain sort of cracks appear. And what we want to try and understand is what are these observation problems pointing at? Because as we see, right, lambda CDM really is like a kind of fitting function. It's a phenomenological model. We're trying to look for a more fundamental pair. And this is where lens supernovae really become crucial in both facets of how supernovae are really important in testing lambda CDM. So where we're seeing potential signs of evolution of dark energy, strong lensing by the sheer sort of magnification of the background source acts as a gravitational telescope. So this is an idea from Fritz Zwicky that basically you're going to be able to study the background source in a lot more detail. So what lens supernovae are going to help us do is understand the high-redshift universe a lot better. And this is going to be important for the dark energies that I'll talk towards the end. And then the second problem, when we're looking at this Hubble tension, lens supernovae provide standard clocks. We're really using the difference in arrival times of multiple images in order to measure the Hubble constant. So it allows us a completely independent way of measuring the present-day expansion rate. And just so that this pretty picture is not there untouched, this is a really key part in the middle, which is the artist's illustration of the leading scenarios of what leads to type 1a supernova. So the point that I really want to make here is that all supernova cosmology is done empirically. We really don't use the information of what is the progenitor or the physical mechanism of the explosion, but it always helps us guide physically how we can understand them better for cosmology. And again, because you have this gravitational telescope effect, understanding their physical mechanism and their sort of explosion properties is really important in order to be able to understand how we can use them better as cosmological indicators. So really, what is this problem of the Hubble tension that we are getting so excited about? So we have absolute distance scales at opposite ends of the observable universe. So we get the sound horizon at the redshift of matter radiation decoupling, and that gives us like an absolute calibration that can be evolved by understanding the expansion history in, like, say, standard lambda CDM scenario, and then with constraints in that sort of region of intermediate redshift, we can get a prediction for the Hubble constant, which is what is the gray histogram in this plot on the right-hand side. Now, that prediction is about 10% lower than the direct measurement from the local distance ladder calibrated to young pulsating stars or Cepheid variables. So that made it very exciting to see what is this tension sort of coming from. And this could be effectively two things. It could either be that our standard model of cosmology, so you're threading the needle through the eye of the universe, which is super cool, is actually, it works really well. But when your uncertainties, like the uncertainties on Planck, is roughly 0.5 kilometer per second per megaparsec, so we're talking better than 1%. And the uncertainties quoted in the local distance ladder are better than 2%. So we're really looking at a greater than 5 sigma tension there. So what people did was they tested sort of, okay, could it be sort of unknown systematics? And in the early universe, when you take away the CMB and actually get the reduced baryon density from primordial deuterium abundance, you still get a low H0. However, when in the local distance ladder, you change the young pulsating variables with older stellar populations, in many analyses, you see that this is in a lot less tension with Planck. It's not in tension with the Cepheid calibrations, but it isn't also in tension with the CMB. So really, what's going on? Are we sort of missing some unknown unknowns, or are we looking at new cosmological physics? And one very powerful way is to have something that's completely independent, that you have supernovae in both the red and the blue histogram. You have local calibration like Gaia parallaxes in the red and blue histogram. We want to do something that is completely independent, so we will know if there are unknown unknowns that we're missing. So we want to look at, like, this is a very mature problem now. We want to look at it from different angles because we're currently stalled and don't have like a clear solution to this Hubble tension. So how has the Hubble constant been measured? And this is to motivate why we want the lens supernovae. So we see, and you might have seen this plot multiple times before, this is from the recent big, or most recent big SHOES release, where there are 42 galaxies, 42 supernovae that are calibrated to these Cepheid variables. And very precisely, the Hubble constant is measured by calibrating the absolute luminosity of the supernovae that are in the nearby Hubble flow, using more close by supernovae that have independent distance indicators. So that's basically the sort of equation here, where you get the intercept of the ridgeline from the distant supernovae given by the second equation, and the absolute value is coming from this rung of the distance ladder. So what this is basically, it's giving you luminosity distances. So it's sensitive to systematics that impact the luminosity. One very subtle point to make here is that these are the supernovae that are predominantly used for the local analysis of H0. But really, they also are the anchor for the high-redshift analysis, where supernovae are being used to understand the properties of dark energy. So these are two very covariant puzzles, and supernovae, both lensed and unlensed, are very central to that problem. Here enter the lens supernovae. Now, how they end up measuring that, when you have, in favorable cases, a massive intervening object between a background source and the observer, you're getting multiple images of the same source. And in this case, these arrive at different times, and those times depend on the expansion of the universe and the gravitational potential of the lens. So crucially here, what they don't depend on is any kind of luminosity distance. So what you end up seeing here is that each of these will correspond to, and I've shown this as a cartoon diagram so that we can see easily they are in different potential channels. So therefore, they have different amplitudes, and they also therefore take different paths in order to come to us. So they are shifted in time. So they're shifted on the X and the Y axis. And when you have a source that has a really nice light curve, you can then start to get the arrival time very precisely. And the point that I really want to drive home is there is no M's and there are no L's for luminosity out here. So this d delta t is just a ratio of 3 angular diameter distances, as you might have seen in your cosmology courses as well. So this is completely independent of the unlensed supernovae. So it gives us a new probe with which we can then start to address this problem. And so, as I had mentioned previously, right, we've gone from what was an idea 50 or 60 years ago to start to become an actual reality. There is a small number of such events that have already been discovered, mainly through ground-based wide field surveys for the ones that are actually lensed by a galaxy, like I showed you previously. But we've also got really fortunate, but have got great data from space, like from the James Webb Space Telescope, to get cluster lens supernovae as well. Galaxy scale lens supernovae are great for cosmology because the galaxy is comparatively much easier to model. So I'll mainly be focusing on the galaxy scale lens supernovae in my talk. But we also learn quite a bit from cluster lens supernovae, as I'll show you in just the next slide. So how have they been discovered? The contrast here is in the previous slide, I showed you the nice multiple images and pasted a cartoon on top of it. Whereas here, you really see that the data is completely unresolved. So how are we able to say that this was actually the image of a lens supernova? And that goes back to what is the other effect of lensing, which is the magnification. So in Gubar et al. 2017, what was seen was that for the first time, we had a lens type 1A where the individual images were resolved. The indication that it was lensed came first from the fact that at a given redshift, this was 4.5 magnitudes brighter. So that suggested already that the lensing effect is coming across as magnification. And that led to further getting spectroscopy. So this was the first spectrum that looked like a type 1A. So the green is at redshift roughly 0. And this is at redshift 0.4. So you can see that when shifted in the redshift axis, they look nearly identical. So it's the type 1A at redshift 0.4. That's giving us an absolute distance, giving us an absolute magnitude, showing us that this is so much brighter than what we expect at that redshift. It also suggested that there's lensing going on because there was a second redshift from the intervening lens galaxy, and that led to getting Hubble Space Telescope imaging, and then you can actually see the multiple images. Now, crucially, unlike other lens sources like lens quasars, which are actually persistently always there, the supernovae fade away. So you can actually get a better lens model by just modeling the host galaxy. You can also get better photometry by doing the subtraction. And because the light curves are so homogeneous across a family of supernovae, you can get very accurate time of peak to get time delays. So that makes lens supernovae really exciting, even within sort of this space of lens transits. And then over the last sort of 1 year, and this was something that I was talking about at every Christmas party since November 2023, was that despite the fact that James Webb Space Telescope has a small field of view, it has been really prolific in finding lens supernovae, specifically ones that are lensed by a foreground cluster of galaxies. Now, while the cluster of galaxies is harder to model, and I will point to other papers which have been very exciting with regards to showing how to measure H0 with this, they're also really exciting for other questions. So questions like, what are type 1A supernovae like in the high redshift universe? And as I said, we want to compare the high and the low redshift universe in order to be able to constrain if there is an evolution of properties. So in 2023, we saw a new source. This was discovered by Drew Newman at the Carnegie Observatories, and it led to follow-up photometric director's discretionary time. But also we had spectroscopy from NIRSPEC. So what this did was it allowed us to get a test of supernova evolution and an independent estimate of the age of the supernova. So that's what we're showing here. So we wanted to test firstly, is this type 1A supernova similar to local type 1A supernovae? So we did a template cross-match with an empirical peak matching software that is used in the community. And we saw that the gray line here, which is the local type 1A supernova, is nearly identical to the violet line that is here, which I think is really cool. I looked at this plot and nearly cried because this is 10.5 billion years of the universe's expansion history. and the 1As look nearly the same. Of course, this shows that these are really good standard candles or standardizable candles across the universe's history. So maybe there aren't any huge sort of shifts in order to get dark energy properties from them in a systematic free way. However, as you can see here, and this is a more quantified way of looking at the line velocities, they are following the trends from the low redshift. So the low redshift is the blue points, and the different length supernovae that we have only a handful of spectra for are actually following the trends. But are there any sort of small shifts? We need samples to actually start to test that. And there was a recent analysis with the same data set of the same supernova, and Justin Perel and my grad student Erin Hayes did a fantastic job measuring the time delays. I will point to that paper. I won't but the error bars are really high, so I'm not going to sort of go into it in that much detail. What was really cool here is that it shows that the silicon velocity follows the evolution, but in order to sort of look for subtle differences, we need large samples. And large samples will be possible now because the Vera C. Rubin Observatory has begun science verification, and the survey should begin by the end of the year approximately. And some work that was done in collaboration with Nikki Arens in the LSST Dark Energy Science collaboration was to look at what do we really expect from LSST, right? We have these one-odd events that we're getting from the ground right now from GWST, but really, we want to try and address the Hubble tension. This is a roughly 10% effect, so we need an uncertainty of about less than 2% in order to measure that at 5 sigma or more. So what we did there was that we took a detailed strategy of how LSST would look at the sky. So this every sort of point is just how many times LSST is looking at a particular patch of the sky. First, it just looks at it uniformly. Then it starts to look at patches in more sort of rolling detail, and that's to get higher cadence light curves. And what we did was we took a set of SED models for type 1a supernovae, along with parameters for the lens galaxy and microlensing maps for deviations from the macro model based on the stellar content of the galaxy. And we made realistic light curves in different filters. And what we saw was how many lens supernovae would be detected. So we actually see about 44 lens type 1As per year. So that's a huge sample when you compare it to the fact that there are only 8 in total right now. So we'll already get an order of magnitude larger in the first sort of few years of LSST. And of them, there will be ones that are bright enough that we can actually get quick spectroscopy, and ones that are discovered before peak, so we can get good time delays. So putting that into a rough estimate of how we expect the Hubble constant, uncertainties per individual object, we can expect to get an independent 1.5% estimate of the Hubble constant in just the first few years of LSST, which is really remarkable and a testament to how amazing these objects are going to be for such a puzzle. But really, this uncertainty, right? We need to work very hard in order to sort of get towards this uncertainty because it includes lots of different terms. And the first term that it really includes is the uncertainty on the actual measurement of the arrival time difference. So this was something that we've been really interested in, which is that on the left-hand side of this equation, you see that it's basically the delta T, the difference in arrival time between any two image pairs. And with this large sample, we're saying, how well can we measure these time delays? What kind of data sets do we need? So there was a detailed set of simulations that was done by my grad student in order to be able to basically get curves that look like this, which is to see the shifted curves for realistic properties of LSST and supernovae, add sort of the ability to measure line of sight effects, and then see how much LSST plus HST data do you need in order to measure them really precisely. And to do that, basically was looking at a simultaneous inference of these chromatic microlensing effects to basically have a Gaussian process on top of the template to look for deviations that can come from any of this line of sight microlensing because of the stars in the lens galaxy itself, as well as to constrain, as we had done for the one object from the ground that had detailed observations, the line of sight dust. So basically, you will have extinction in each individual line of sight. And we want to constrain that simultaneously with the time delays because we don't want the time delays to be biased by the dust extinction. So the code does all of that in one go, but sometimes the LSST data might not be enough in order to constrain all of that. So what Erin did, and details are in this paper, is that she simulated detailed multi-band cadence light curves in a similar way to what we did for Nikki's paper, and then simulated follow-up from HST. So you can see HST optical and HST near infrared. And we took realistic observing strategies like how well can we schedule HST, what filters can we get, and what is a realistic signal to noise that we can get in one orbit of HST for each E. We then specifically tested the faint end of the detectable LSST simulation. So this was focused on objects that are roughly 22 to 22.5 magnitude in LSST, because we're like, if we can measure these really well, the brighter ones will just be easier. So let us design our observing strategy in a very conservative way. And we took only like 6 epochs. And then with different LSST positions on the sky, we basically looked at how well can you measure the uncertainty. And what we saw was that we can measure the uncertainty in the time delays with just a few epochs to 5% or better. And this is really important because this makes it subdominant to any of the uncertainties in the lens mass model. So this gives us how we can design our observing strategies for the first LSST discoveries based on very detailed simulations. What we also found was that if you take type 1a supernovae that are actually truly from one kind of empirical model and model them with another model, as we try to realistically get an uncertainty budget, we get about a 2.5 just from that. So improving the type 1a models is going to be one of the main sources of uncertainties that we need to overcome to even get better time delays from these handful of epochs. So that gives us a full spectrum of how we need to do the observations in order to get precise time delays from lens supernovae. So how do we move forward? This is basically showing you how we can get good uncertainties from deep ground-based and deep HST follow-up. And what we see here is the thing that I was mentioning previously, that we can get to sub 5% when we have just a handful of HST epochs. We can also, because of the HST near infrared, start to get very accurate constraints on the image magnification. And the image magnification is going to be really important to break modeling degeneracies like the mass sheet transformation, because type 1a supernovae are all of nearly the same brightness after standardization. So this is something that's really important when we are starting to devise what the strategy is going to be for following up LSST supernovae. So this is showing you the importance of just a handful of space-based epochs compared to a more detailed ground-based light curve when we are looking at the comparison of two different observing strategies. So if you ever have an HST proposal for lens supernovae, this is the paper that you should go to in order to start to run the piece of code and get your time delay uncertainties out. And then when we actually have the discoveries, we will be applying this in order to do the final time delay inference with systematic uncertainty. So really, when you have two grad students and an equation with two terms, you get one of them to work on the left-hand side and the other one to work on the right-hand side. So since we've been looking at the time delays with Erin, my student Zeph has been looking at the other side, which is basically the second part to calibrate in order to get the Hubble constant. And this basically, and you might have seen this in cosmology lectures, so this is just, I'm just going to go very briefly through this so that we know what quantities we're looking at. So this is giving you the lensing potential and then the Fermat potential. And this, all of the physics of lensing is basically in the fact that your deflection angle is a function of the position. And you basically have the second derivative of your Fermat potential is your convergence, and that is just the 2D projected density. Now, people have been using sort of a very simple isothermal sphere or isothermal ellipse, like we see for galaxy rotation curves, in order to get the 2D projected density. However, when we want to get a really precise sort of, we want to achieve that uncertainty of 1.5%, right? We need to see whether or not this is sufficient, because real galaxies are probably not going to be that simple. So what has already been done, and this is an example from the first resolved lens type 1A, is that we're not just using like image positions. Now lens modeling is actually using a full like prescription for the lens light of the galaxy, the full sort of explanation of how the host light is as a function of radius. And then you see a combination of the lens host light and the individual point sources are being modeled, for example, in this case, for the first resolved lens type 1A. So in this detailed model, you can see that like as of now, the power law with ellipticity, so this is what I'll show you in the next slide, works really well in order to be able to get the lens potential. So this is what we're seeing here. I hope this, yeah. So what we're seeing here is just the intensity profile. So depending on whether or not it's steep or shallow, you just see how this 2D density like moves away from the center. But that's just giving you what the radial angle is. So that's just telling you how it radially changes. It doesn't tell you about the angular structure. Real massive ellipticals can have some level of boxy or diskiness. And that boxy or diskiness, which is going from like more disky to more boxy galaxies, is what we're seeing here in this case. This is typically not accounted for when we are doing lens modeling. So far, that for the uncertainties that we've been getting, like we don't have very precise time delays, we aren't really looking at this as a systematic. But when we're talking about 1.5%, this is going to start to become a really important source of the uncertainty budget. So what Zed has been looking into is actually adding this complexity in your phi multiple. So basically, your lensing potential starts to have higher order terms that are capturing this boxy and disky profile. And what he's seeing here is basically that when you, so this is an example of what you have as the amount of boxiness or the amount of diskiness is just showing 3% and 5%, which is within the realistic distribution. You can then sort of, this is just showing that like when you put in a level of boxiness, your model is able to recover it and get normalized residuals. But when you're starting to ignore this, so what he's basically doing is injecting this into the true galaxy simulation and then trying to recover it without any of the boxiness like is done currently in the literature. And you see these huge residuals that are there in different aspects of like the lens post galaxy. He then ran this whole thing all the way out to H0, and what he saw was that for these typical 3% multiple strengths, you can start to get quite a significant bias in what the inferred value of the Hubble constant is, which is really showing that this kind of angular structure is critical when we are trying to understand what the total systematic and statistical uncertainty is. Therefore, this should be taken into account in all data that we get as high-resolution images of the lens supernova. What he's currently doing, which is the paper that's in prep, is then testing this out against realistic n-body simulations of galaxies and seeing what level of boxiness and diskiness is actually allowed from these end-to-end simulations of the low redshift to intermediate redshift universe. So this is really helping us quantify what are the different sources of uncertainty when we're using lens supernovae for cosmographic probes. The last thing I'll talk about, which is very exciting from the standpoint of using them as gravitational telescopes, is that lens supernovae are also really important for dark energy constraints. And this will involve more GIFs, and some of them I've actually annoyed my friends by sharing them on WhatsApp, but I really enjoy sharing W0W with. So apologies for lots of W0W thoughts that will follow. What we have been seeing recently, and this is the other place where lensing is going to be really important, is that in this high redshift end of the Hubble diagram, the lens supernovae, they're going to be much brighter, so we're not going to be able to use distances really well. But because they're brighter, we'll be able to get very high quality data to study them in detail. And the question is, when we're using the type 1A supernova Hubble diagram in order to measure cosmology, we're comparing the blue to the red. So any differences that are coming either because of instrumental systematics or because of astrophysical systematics between the blue and the red can be things that are actually shifting from our true cosmology. So what we want to do is we want to see, are there any sources that can explain shifts from a true cosmology that are comparable to what is seen in the BAO plus CME plus supernovae. So what we're trying to say is, how different do the blue and red need to be? And then what lensing can help us with is actually testing out in detail what the blue points look like, because then we get really good quality data. So we basically just sat down once and drew lines on a piece of paper and then coded them up. But each of them was motivated by a physical effect. So when we're going back here, right, the red ones are observed by lots of different old systems that are not really as well calibrated, except maybe one. And a lot of these objects are actually really well calibrated. So if there's any calibration uncertainty that's there between these two, we will see that as a sort of step function in the distance. So we just took very sort of phenomenological prescriptions for how the Hubble residuals change as a function of redshift. We took particular changes that happen if, say, type 1a supernovae are slightly different between the high and low redshift. And we wanted to see how different do they need to be. What we also did was we looked at this particular case, which is this orange line. And that orange line corresponds to the dust in our own Milky Way. So we've been correcting the dust in our own Milky Way using quite an old dust law from the 80s, sometime in the late 90s. But that dust law has evolved over time with better data sets, with better understanding of the local population of stars. And we wanted to see, okay, if we use a more updated dust law, how much does that actually change the distances? So that is what the orange line is showing us. And this is what I was saying with regards to the progenitor evolution, which is basically showing you what if the type 1a supernova population is actually not the same at redshift roughly 0.05 as it is at 0.5 or at redshift 1, and that would probably manifest as some kind of a change in the Hubble residual. So what we did as a result was we looked at if the true cosmology, let's just take that the true cosmology is lambda CDM, then we add certain effects. So what we did was we said, what if we start adding more calibration effects? At what point do we start to see it sort of agree with what DESI plus DES plus the CMB finds? So the points here are the three central points of those ellipses that we had. And we take this to be the fiducial cosmology. And if we have an offset of about 5/100ths of a magnitude and a dust law that's more updated, those changes in the distance from these systematics can actually push the data in this direction along to the best fit cosmology that we get from DES plus DESI plus the CMB. Now, one way of testing this would be to then have a new low redshift sample, which is much better calibrated. So this is some work that has been done in detail in ZPF with its second data release that came out last year to earlier this year, was in a special ANA issue. And this can also be done by actually using a updated dust law when we're doing the full cosmological analysis. So there are ways to now have a test of what kind of systematics could be causing this kind of shift. And it would be really important now to either do the reanalysis or have new samples to see whether this is a sign of non-standard dark energy properties or whether this is actually suggesting that this is due to systematic uncertainties being either subdominant or something that is, or either systematic uncertainties underestimated, or whether it is because we just didn't know about a more updated dust law that can actually be causing shifts in our cosmological inference. So what I would like to advertise is we have a very nifty Python tool. You can just run a widget and you can play around with different effects, make your own GIFs, and just see how these contours shifts with the different effects that we have tried. So you can say, okay, maybe it's progenitor evolution of this kind plus some other uncertainty from either calibration or dust. And then we can actually see what we need to test with next generation surveys to be able to either confirm or refute this evolving dark energy scenario. So in this case, of course, lensing is going to be really impactful, but so are going to be unlensed type 1 supernovae from more modern surveys. So I'm going to leave you with my conclusions. So potential systematics are really important when we're trying to analyze the dark energy data, and this is where lensing is going to be important for the high redshift universe. And we don't really see any sort of strong evolution from this single supernova encore, but the large sample of LSST will be really important to constrain this better. And we can get sub 5% time delays with the Hubble Space Telescope with just a few epochs. And it's important to constrain the lens modeling systematics for the angular structure if we want to get precision cosmology from the time delays of lens supernovae. So thank you for your attention. I'm really happy to take questions.
Thank you very much for the. So we can start with the question. So is there any question? Yes.
Thank you for the talk. I have two questions. The first is maybe can you explain more why the time delayed distance is related to the H naught? It's not quite clear to me. And the second question is very clear, like as you mentioned, okay. In the previous slide, you mentioned the high redshift supernovas have a well calibration, but the local one does not have the very good calibration. I don't quite understand why the local one has worse calibration. Yeah, that's my question.
Both excellent questions. So you can see from basically just the lens equation that when you're the two things that your time delay distance, which is just the ratio of these distances, will depend on is the difference. And so you're basically taking separate paths where in this particular case. And it's really what are those separate paths dependent on? It's how much the universe has expanded. So that's giving you the H naught. So that's the ratio of the distances. And it also depends on what the basically the gravitational potential of the galaxy is. So if that's from a different sort of part of your main deflector, then you're going to get, like, let's say the potential is higher, so it'll take longer to come to you. So those are just the two sort of components upon which the light path will depend. So for the same, say for example, to get the same time delay, you can either have the universe expand faster, or you can have the potential be lower. And that's effectively all that the equation is saying. So that's how it depends, the time delay depends on cosmology. And to your second question, which is a great question, and I will point, I think the Hubble diagram would be quite illustrative because really, so this is all coming from a single survey, the dark energy survey with the DE-CAM. Louis is the in-house expert on this. And because everything was observed with a single telescope that was well calibrated, it's comparatively easier to get good distances. Whereas previously, in the low redshift universe, it was all done with much older telescopes that were not as well calibrated. But the reason is also when you're looking at local universe, the volume is just lower. So if you want to build statistics, you need many different surveys, and everyone is kind of doing their own thing. So you can't get a very large sample with a single telescope. You really need it to be wide and somewhat deep to cover large area and to cover depth and redshift. And that's why it's only been possible with modern surveys like CTR. So surveys up till say late 2000s were really just 100 supernovae on one, with one patch of the sky, or using one particular sample of galaxies to target, for example. So that's why you don't have as good a handle on this to get the full sample. Volume effects, and it was older samples.
Thank you. Is there any other question?
Thanks. Very nice talk. I was very impressed by the 1.5% expectation reached out here on the first year's LSST data. I wanted to ask, given these nice potential that you're expecting, do you think not just strong lenses, but big lens effects along the line of sight might start to be an issue? You discussed very much about the potential of the lens galaxy, but what about everything that's between? Are you thinking on that?
Yeah, so one of the things that we can do is, so I don't know if the plot is necessarily the best thing, but yes, is the answer. So the two components in the cosmography that I've shown are sort of the, sure. but yeah, the point is that this equation is actually a little bit simplified because the external convergence from like the line of sight structure is also important. So what we've mainly been focusing on is things related to the supernova and the main deflector system. But what is also done is like you take the galaxy number counts and you calibrate an n-body simulation to get the line of sight structure. So that is in the sort of final systematic error. One thing that we can do with supernova is also we can like get a level of sort of the mass sheet degeneracy. So any kind of systematic where you'll have a uniform sheet of mass that could be like just biasing your time delays and therefore H naught. And what supernovae like of type 1a do is they give you an absolute flux calibration because you're like, okay, if this is supposed to be 19th mag and it's actually 22nd mag, I know what my magnification is in linear scale. And then I can basically, based on that, say how much this mass sheet transformation is. So it kind of gives you like with an independent way of breaking modeling degeneracies as well. But yeah, so those are the two ways in which we do this problem. Yeah.
Thank you. Any other question? So I have one question, so not at all my field, but in some years there will be the Nancy Grace Roman telescope. So
Yeah.
you expect any interesting data that mission?
Yeah, so both for, so one thing that would be there is like, oops, sorry. That was, but yeah, so today on the ground, you see the Hubble diagram that goes to about redshift 1, and Roman is going to push it out to about redshift 2 with like a large statistical sample as well. So it's going to definitely like allow us to get much better W0 WA constraints. It's also going to have infrared filters, so therefore we're going to be able to even like on some hierarchical level simultaneously constrain dust properties as well, so minimize that systematic. For lens supernovae, what Roman will be really, really amazing for is because it's from space, the resolution will be much better and you're going to be able to see the multiple images in the discovery data. So not all Rubin objects will be resolved, but in Roman, all of them will be resolved. So that is something that will be like you can always just get 90 days without needing an HST or AWST. So that's where it will be really useful.
Okay, thanks. Okay, so if there's no more questions, then we can thank you again. Have to go to the pizza, so remember, don't start eating the pizza because the speaker is joining. By the way, is there any